question 3 says the frequency f of the fundamental vibration of a standing wave of fixed length is measured for different values of tension in the string using the apparatus shown. Now, for those of you that do high-level physics, when we set up standing waves, the fundamental frequency for this, the fundamental waveform is one like this. It's just you basically get half a wavelength in that string and it vibrates to and fro like that. You don't actually need to know that to answer the question. Just got to be able to work with the information. So in order to find the relationship between the speed v of the wave and the tension T in the string, the speed is calculated from the following relationship, that v is equal to 2 times the frequency times the length. We don't need to really worry about that formula. So, where L is the length of the string. The data points are shown plotted on the axes below. The uncertainty in V is plus minus 5 meters per second to negative 1, and the uncertainty in T is negligible. Draw error bars on the first and the last data points to show the uncertainty in the speed V. So we have this as plus minus 5 meters per second. And what you need to do in putting it, so we're going to be doing it on this data point over here, that one there, and that one over there. Now we've got to go plus minus 5. Now it's important to see what is the value of a small block here. How much is a small block? Well, we can see we're going from 0 to 10 in 5 small blocks. So each small block is worth 2 meters per second. So 5 meters per second will equal 2.5 small blocks. So on either side of this point, we've got to go 2.5 small blocks. Now you'll be able to do this better than me because on my whiteboard it's not really easy to be very accurate. But you've got something like that, and on each side you're going 2.5 small blocks. Albeit says the original hypothesis is that the speed is directly proportional to the tension T. Explain why the data do not support the hypothesis. So when you're talking about directly proportional, that V is directly proportional to T, you would have this formula, y is equal to mx. It's a straight line going through the origin. In that case, for instance, we would have V is equal to some constant times T, where this constant is the slope. Now, looking at the data here, I can see if I had to draw a best fit line, I would probably be drawing some sort of curve like that, certainly not a straight line, and not going through the origin. So you'd put those 2 points. It's not the best fit line. The best fit line is not straight and not through 0, 0, not through the origin. So those would be your reasons for that. So here we have, in the second part, it is suggested that the relationship between speed and tension is of the form V is equal to K square root of T. V is equal to K the square root of T, where K is a constant. To test whether the data supports this relationship, a graph of V squared against T is plotted and shown below. Now, why V squared? Well, what's happened here is we've changed this into V squared is equal to K squared T. And if we think of my proportional graph, y is equal to mx, y is v squared, and x is t, and your slope of your graph will be k squared. So it says the best fit line shown takes into account the uncertainties for each of the points. The uncertainty in v squared for t to the t 3.5 newtons is shown as an error bar on the graph. state the value of the uncertainty for v squared for t is equal to 3.5. So looking at this is our error bar here. It's going from there. So this part over here will be half of it. Half of that error bar will be your uncertainty. So it's going from 2.1 to 1.6. So it's going to be 0.5. But notice this multiply here. This is times 10 to the 3. So it's times 10 to the 3. So that's going to equal 500. Now the units for this are going to be meters squared s to the minus 2. So that will be your plus minus value for your uncertainty. 500 meters squared s to the minus 2. It then says at t is equal to 1 Newton, the speed is 27 plus minus 5 meters per second. Calculate the uncertainty in v squared. Now, in doing this, we need to remember our formula for that. We're going to use this formula over here. Now, we want to calculate our uncertainty in v squared. So, if I use this formula where we have multiplication and division, we know that v squared is equal to v times v. So, I can work out what my v squared is. That's going to be 27 times 27 squared. Now, putting it into this formula, I'm going to get my error, my absolute value error for v squared divided by v squared is going to equal my error in v over v plus my error in v over v. So, I'm going to get my absolute value error for v squared is going to be 27 squared, like that, times, and this over here is 5 over 27 plus 5 over 27. So when we calculate that all out, we can use our calculators. Obviously 5 over 27 plus 5 over 27 is 2 times 5 over 27, which is 10 over 27 times 27 squared. My 27 can cancel out there, and I'm going to get 270 will be my error for v squared, and that is going to be meters squared s to the minus 2. So that will be that value over there, giving you your 3 marks. Question D, it says use the graph in C to determine K without its uncertainty. Now we know that for this graph, it's a graph of v squared is equal to k squared t. So when we plotted this over here, this k squared is the slope of the graph. Remember, y is equal to mx. We have the m is the slope. So we have to find the slope of this graph. Now when doing this, you want to use the largest amount possible of the graph. So I'm actually going to use this triangle over here. I'm going to use from there to there. You've got to use as most of the graph as possible. And your slope is always your change. This will be your change in v squared over your change in t. That is going to equal k squared. So k squared is going to equal, now this over here, and going up here, each one of these is, this will be 2.6, so it's about 2.55 there, going up. I'm looking at the vertical, I'm looking at this over here. I'm about 2.55, but remember it's times 10 to the 3, so it's times 10 to the 3 divided by my base here, this over here, which is 4. I chose that specifically so that I had a whole number value there. So we put that into our calculators. So we get 2.55, 2.55, and I find 10 to the 3, put 10 to the 3, divided by 4, and I get a value of 637.5. But now I have to take the square root. I actually want to find the value of k, so I need to take the square root of that. So take the square root of my answer, and I get a value of about 25.2. Now, for this, in looking at the units, there's different ways of putting your units. But if you just go straight to these over here, we know that for this is going to be meters squared s to the minus 2 over newtons, because you've got your newtons here and your meters squared s to the minus 2. So when you take the square root of that, it's going to be meters s to the minus 1 newtons to the half. So we could write it like that if you want to do. There's other ways of doing it, but that would be fine.